we're solving this equation for some potential, and since H is Hermitian, we have the results that we mentioned last time. That is, the eigenfunctions of H are going to form an orthonormal set of functions that span the space. You can expand anything on them. This is what we prove for a general Hermitian operator to some degree. So the eigenfunctions form an orthonormal set that spans the space. So you're going to find a psi 1 with an E1, a psi 2 with an E2, and then this continues. And this is called the spectrum of the theory. Because energy eigenstates are considered the gold standard. If you want to find, solving a theory means finding the energy eigenstates. Because if you find the energy eigenstates, you can solve, you can write any wave function as superposition of energy eigenstates and then just let them evolve. And the energy eigenstates evolve easily because they are just stationary states. So the spectrum of the theory is the collection of numbers that are the allowed energies. And of course the associated eigenfunctions. So the energies may be many, may be discrete, maybe there has a little bit of continuous part, there's all kind of varieties. But your task is to find those for any problem. So the equation that we're trying to solve is now rewritten because we're going to try to solve it. So let's look at it. It's a second order differential equation with a potential in general. So we had it somewhere there. It's there. It's boxed. So we'll write it slightly different. We move the potential to the right-hand side and get rid of the constants here. So squared. Okay, so this is the equation we have to solve. So whenever you have a problem, you may encounter a potential, V of x. And the question is how bad this potential can be. Well, the potential may be nice and simple. Or it may be nice, but then have some jumps. It may have infinite jumps. like a potential, it's a complete barrier, or it may have delta functions. All these are v of x, possible. V of x, all of them. Many things can happen with the potential. In fact, the potential can be as strange as you want, depending on what problems you want to solve. So it's your choice. Now, we are going to accept, in fact, all of those potentials for our analysis. May be nice and smooth. They may have discontinuities. They may have infinite discontinuities, and worse things like delta functions. But worse things than that, we will ignore. And there are worse things like that. Maybe a potential is discontinuous at every point, or maybe a potential that has delta functions and derivatives of delta functions, or potentials that blow up and do all kinds of things. But this is, and I'm not saying you should never consider that. I'm saying that we don't know of any very useful case where you get anything interesting with that. But it's conceivable that a particular kind of singular potential one day could be interesting. So we'll look at these potentials and try to understand. We try to understand how to set up boundary conditions. And we're going to worry about basically psi and how does it behave. And my first claim is that psi of x has to be continuous. So psi of x cannot jump. The wave function move along but cannot jump. And the reason is the differential equation. Look, if psi of x was not continuous, if psi of x was like this, it just had a discontinuity. If psi of x is like this, psi prime of x would contain a delta function at this discontinuity. The derivative is infinite. And psi double prime of x, the second derivative, would have a derivative of a delta function, which is worse, because a delta function, we think of it as a spike that is becoming thinner and higher, but the derivative of the delta function first goes to infinity and then goes to minus infinity and then comes back. It's much worse in many ways. And look, if you have this differential equation and psi is not continuous, well, the right-hand side is not continuous, or it may have a delta function times something not continuous, but the left-hand side would have a derivative of a delta function that there's nowhere on the right-hand side. On the right-hand side, the worst thing that could exist is a delta function in v of x. But a derivative of a delta function doesn't exist, so you cannot afford to have a psi that is discontinuous. Psi has to be continuous. There's other ways to argue this. I might put them in the notes, but I'll leave it like that. Now, how about the next case? I will say the following happens too, that psi prime of x is continuous unless v of x has a delta function. You see, potentials with delta functions are nice, they're interesting. We will consider them. Delta function potentials can be attractive potentials, repulsive potentials, they're quite interesting. So I claim now that psi prime of x has to also be continuous. Why are we worrying about psi and psi prime? It's because you need two conditions whenever you're going to solve this differential equation at an interface. You will need to know if psi is continuous and psi prime is continuous because it's a second order differential equation. So suppose psi prime is continuous, then there's no problem. If psi prime is continuous, the worst that it can happen is that the second derivative is discontinuous. And the second derivative is discontinuous could happen with a potential that is discontinuous. So, no problem if psi prime is continuous. But psi prime can fail to be continuous if the potential has a delta function. And let's see that. If psi prime is discontinuous, then psi double prime is proportional to a delta function. If psi prime is discontinuous, double prime is proportional to a delta function. But here, psi just takes some value. There's nothing strange about it. In order to a delta function, which is psi double prime, to be equal to this right-hand side, v of x must have a delta function. If psi is continuous, and v will have a delta function. So it will be a somewhat singular potential, but we're going to look at them in about a week from now. But this will be our guidance to solve problems. The continuity of the wave function and the continuity of the derivative of the wave function. And for these slightly more complicated problems in which the potential has a delta function, then you will have a discontinuity in psi prime, and it will be calculable, and it's manageable, and it's all very nice. Now it looks a little complicated, and everything is kind of mixed up, but you will see that it's quite doable.